Hi everyone, welcome to my YouTube channel. In this video series, we are planning to talk about the application of statistical methods in manufacturing industry. Please subscribe to this channel to get notified when a new video is released. In this video, we will be learning about the Weibull distribution, which is one of the important continuous distributions. The Weibull distribution has been used extensively in reliability engineering as a mathematical model of time to failure for electrical and mechanical components and systems. Examples of situations in which the Weibull distribution has been used include electronic devices such as memory elements or mechanical components such as bearings, structural elements in aircraft and vehicles. It can also feed a huge range of data from many other fields like economics, hydrology, biology, engineering sciences, but it is frequently used to model the reliability, survival, or anywhere which time to failure is important. It is also used in warranty analysis and utility services, or for lifetime analysis of dental and medical implants. The failure area and reliable area are shown on the PDF graph. The only reason to use the Weibull distribution is because of its flexibility. It can simulate various distributions like normal and exponential distributions. By appropriate selection of the parameters, it can take a variety of shapes. Several Weibull distributions by different parameters are shown in this graph. Look at the upper right figure, which shows Weibull distributions with different parameters. Two main parameters are shape parameter, which is a gamma, and a scale parameter, which is alpha. You can see that how shape and scale parameter could change the plot. For example, for the shape parameter gamma equal to 2, when the scale parameter alpha changed from 1 to 2, see how the plot gets expanded and the mean gets shifted. The lower plot shows the cumulative distribution function, CDF, which provides the probability of failure up to a specific time. The CDF value at a specific time is equivalent to summation of all probabilities below that specific time. Or, in another word, we can say it is the area under the Weibull PDF function. Note that the CDF is the integral of PDF, or PDF is the derivative of CDF relative to time. There are two versions of Weibull probability density function, 2-parameter PDF and 3-parameter PDF. Here is the 3-parameter PDF with shape parameter gamma, a scale parameter alpha, and the location parameter mu. The second version of Weibull distribution is 2-parameter PDF, which the formula is practically similar to the 3-parameter Weibull, except that location parameter mu is equal to 0. In both versions, the shape and scale parameters are bigger than 0. The location parameter mu just changed the location of Weibull distribution along the x-axis. It moves the whole graph to the right or to the left. There is another version of Weibull distribution which is derived from a 2-parameter PDF, which mu is equal to 0 and scale parameter alpha is equal to 1. And here are the mean and variance of Weibull distribution. Please note that this is the gamma function in both equations. You don't need to worry about how to calculate gamma function by hand. There are many tools like MATLAB and Minitab which help us to easily calculate the gamma value and mean and the variance. The cumulative distribution function provides the probability of failure up to the time A. The y-axis value equivalent to area under the PDF. This is the red area or the failure area. The time after the time A is the reliable area, or this green area. Could be calculated from this equation, which is the total area under the PDF curve, which is 1, minus the failure area, the red area. This is called the reliable area. Let's switch to MATLAB. and do some calculation there. Suppose you want to simulate the tensile strain data of a thin filament using a Weibull distribution with the scale parameter value 0.5 and the shape parameter value 2. Also, we would like to see how the curve is changed when the shape and the scale parameters vary. Okay, so let's look at this code. The gamma is 2 and the alpha is 2 as well. The time is changing between 0 to 5 hours with a step 0.1 hours. Here is the PDF function that we discussed earlier, and this is the CDF. Let's plot both of them with subplot and plot functions. When we run this code, we will get this figure. The top one is PDF and the lower one is the CDF. Now I want to show you how PDF and CDF vary with different shape and scale parameters. Okay, let's go here. Here, gamma can take values 0.1, 0.5, 1, and 2. Alpha can take values of 1 and 2. And time is changing between 0 to 10 with a step value of 0.1. Here I have used a 2 for loop. So, and this is the PDF function, and this is a CDF, and 2 subplots to plot the fx, which is our PDF function, and the CDF here. And here is the legend equivalent to gamma 0.1 and alpha equal to 1, gamma equal to 0.1, and alpha is equal to 2. That's the same way that this one is changing. A statistics and machine learning toolbox in MATLAB offers several ways to work with Weibull distribution and fit Weibull distribution to data and estimate parameters including scale and shape parameter, mean, and variance. Let's generate a single random number from the Weibull distribution with a scale 2 and shape 2 with a Weibull random number. Okay, here's a Weibull random number generator. It takes the alpha, our scale parameter, and the gamma, our shape parameter, and it will generate a random number. So let's run this one. It generates a number from the Weibull distribution with these parameters. We can also create a vector of random numbers with these functions in MATLAB. Okay, so the alpha is equal to 2, gamma 2, and the vector is 1000 by 1. We are using the Weibull random generator, which takes the alpha and gamma and also the vector size. And here's the time is defined. And we're plotting the R2 is our randomly generated numbers and X label and Y label. Let's run this code. Here it shows the randomly generated numbers from the Weibull random generator. Now assume we have some random numbers generated. We would like to estimate the Weibull distribution parameters, shape, and scale with the given sample data. We use this one. Okay, and we can run this part. So 1.95, 1.93. These are the values for the alpha and gamma. We can also use Weibull plot to create Weibull probability plot comparing the distribution of the data in X to the Weibull distribution. Let's run this one. Here is the Weibull probability plot, which is close to a straight line. To calculate Weibull mean and variance, write this line of codes. Run this part of code. The mean value is 1.77 and the variance is 0.86. The probability density function of Weibull distribution with a scale parameter alpha and shape parameter gamma could be evaluated at the values in time with Weibull PDF. So let's write that code here. So it takes a time, alpha and gamma, and so then you can plot the fx. Let's run this part of code. Here is the probability density function. We can also compute the CDF of Weibull distribution with the scale parameter and the shape parameter. Here's the code. We're using the Weibull CDF. It takes time, alpha and gamma, and the result is going to the y, and we plot the y relative to the time. Let's run the code, and here is the CDF. Now assume the location parameter is 5. Okay, so this is the Weibull random generator, which is the alpha is 2, gamma is 2, and the vector is a 1 by 1000. And this is the location parameter. So the whole Weibull distribution is shifted 5 units. And here is a histogram of data. Let's run this code. So here it shows the distribution of these numbers. As you can see, it's starting from the 5 in x-axis. We can shift this data to 0, to the origin. So data value that we generated here, -5, we'll save it in the data 2, and we can see how the Weibull plot looks like. So it's completely linear, and it fits to a straight line. And let's look at the histogram with the fitted Weibull distribution. There are other ways to create Weibull distribution in MATLAB. We can create a Weibull distribution object using a default parameter values. We can make a Weibull distribution with default parameters. Let's run this part. Default parameters are 1 and 1 for both the scale parameter and shape parameters. We can create a Weibull distribution object using a shape parameter 2 and a scale parameter 2. Let's run this part. A is equal to 2 and B is equal to 2. We can change this one to the 1 and run it one more time. Okay. We can generate the random numbers from the distribution. This is here we are creating a random number from these probability density function that we created. We can construct a histogram using 100 beans with a Weibull distribution fit. Let's run this part. So as you can see how the histogram looks like. We can compute the PDF values for Weibull distribution at values in x. For example, x here is time. It's changing between 0 and 6 with a step value of 0.01. Here's the probability density function. It takes the probability density function that we created before, and it's taking the time values. So it will generate the probability density function. Then we can plot it. Let's run this part. It shows us how the probability density function looks like. As you know, to calculate the failure rate of such function, we need to take the derivative of this function with respect to time. When the gamma is equal to 1, then the coefficient of exponential becomes a constant number. When the gamma is equal to 1, the failure rate is constant. If the gamma is more than 1, the failure rate increases with time. And obviously, with gamma less than 1, the failure rate decreases with time. Let's look at display panel lifetime calculation by Weibull distribution. The time to failure for an electronic component used in a flat panel display unit is satisfactorily modeled by a Weibull distribution with shape parameter 0.5 and a scale parameter 5000. Find the fraction of components that are expected to survive beyond 20,000 hours. Also need to find the fraction of components that are expected to survive below 10,000 hours. We also need to find the fraction of components are expected to survive between 10,000 and 20,000 hours. And finally, find the expected time to failure. Let's do all calculation in MATLAB. Okay, the scale parameter is 5000 and the shape parameter is 0.5. The fraction of components expected to survive beyond 20,000 hours is equal to 1 minus the probability of the survival less than 20,000 hours and can be computed by CDF function in MATLAB. The result shows almost 14% of sub-assemblies will fail by 20,000 hours and 86% survive until 20,000 hours. To calculate the expected time to failure, we can use Weibull stat function. As you can see, the mean or expected time to failure is 10,000 hours. Okay, let's plot the probability distribution function and cumulative distribution function for these scale and shape parameter. Here it is. Let's do another example. Suppose you are a manufacturer of tires and customer asks you for 20,000 tires. Customer asks you what percent of tires are likely to fail within the warranty period of 6,000 kilometers. Based on previous data that you have collected, you know that the shape parameter is 3.5 and the scale parameter is 5,000. You can easily answer this question. What percent of tires are likely to fail within the warranty of 6,000 kilometers? You could answer this question in MATLAB. Let's write this code in the script file. The gamma is 3.5 and the scale parameter is 5,000. Total tires are 20,000. To answer these questions, we have used CDF function, which gives us cumulative probability which tires fail within 6,000 kilometers. In total, 85% of tires are likely to fail before 6,000 kilometers. Here are the PDF and CDF functions for this example. The area below 6,000 is the failure area, and the area above 6,000 kilometers is the reliable area. Let's plot this in Minitab. Go to Graph, then Probability Distribution Plot, select Vary Parameters. We can have multiple distribution by changing the shape parameter. The shape parameter describes how your data are distributed. A low value for shape, say 1, gives a right skewed curve. A high value for shape, say 10, gives a left skewed curve. We can also visualize the effect of a scale parameter on Weibull PDF plots. Let's select 1,000, 2,000, 5,000, and 10,000 for a scale, and 3.5 for shape parameter. The PDF plots look like this graph. When the scale parameter increases, the mean is shifted to the right. We can also easily answer the question in Minitab. What percent of tires are likely to fail within the warranty of 6,000 kilometers? Go to Graph and then select Probability Distribution Plot. Then select View Probability. Select Weibull. Put the 3.5 for shape. For the scale 5,000. and threshold 0. Select Shaded Area tab, and then select X value and right tail. For the X value, enter the value of 6,000. As the result says, in total 85% of tires are likely to fail before 6,000 kilometers, and just 15% will survive. Alright, this video covered Weibull distribution. If you like this video, please don't forget to subscribe to my channel and leave your comments below. We will continue to make such videos for you. We are going to release video series on different topics, including application of statistics in manufacturing and quality control, robotics and mechatronics, industrial machine vision, system dynamics, finite element analysis with abacus, GD&T and tolerance analysis, and many other interesting topics. Don't forget to subscribe to this YouTube channel to get notified when a new video on this topic is released.